All right, good afternoon, colleagues. Good evening, sorry. Believe you
Good
guys can
afternoon,
hear.
sir.
Okay,
Evening,
hi,
sir.
hi. Well, the power came just back on time. Yeah, so we're gonna begin shortly. Let me just open a new notebook here. Um, okay. Um, oh, all right, colleagues, we're gonna begin now, no? Okay, let me just quickly share, and then I'm gonna move. So get your pen, calculate, and so on ready. And I'll begin immediately. Just let the people in if you can. Okay, so just have a look here. Functions 112. Okay, so what I'm gonna do before we embark on the theory part here, right? See this introduction. I want to skip right into 4.2, 4.3, 4.4. Is that fine with everyone?
Okay.
Richard?
Yes.
Yeah, okay. Um, it's so
Yes, sir.
the reason why Tanukaji Dalmuri Heinrich Eshonai is because I want to get into the calculation part first, man. You know what I'm trying to say to you.
Okay.
The actual doing first. And as I do, I can always revert back to the 4.1. You know what I'm trying to say to you, which is basically we fine. So as I do the questions in, maybe if a question does arise related to 4.1, you guys can ask. So I wanted to go through 4.1 and go to 4.2, but I wanted to get into the hands-on stuff first, man. Is that fine? Or I can just go in order, you know what I mean? It's not really a big deal. It's quite straightforward. It's just me talking, but I believe okay, let me just go through 4.1 and then I'll do 4.2. Okay, can we proceed?
Yes.
Yeah,
Yes, sir.
and if you're uncertain at any point, you can just let me know. But 4.1 is going to be basically me talking.
Okay.
Okay, let me do this quickly. Let me be my normal creative self here. Let me just do my normal creative self here. Okay, just give me a second. So I'm just opening something else quickly. Okay, I found it. Okay. Yeah. So this is what I actually planned until this whole thing threw me off. But anyway, let me do what I initially planned. So I'm opening up Excel. You guys familiar with Excel?
Yeah.
As a professional, you should be, right?
Not
Okay,
as
so
smooth, but okay.
yeah, okay. Well, if you're even interested, you can always ask me for some help. Well, I'm not a so-called expert, but I know my way around certain stuff here. But nevertheless, what you're currently seeing here is a spreadsheet, right? Which is able to calculate the performance of something called a flat plate solar collector. This is part of my expert.
Excuse,
I can't
Yeah,
see anything, sir.
yeah,
you
we
can't
can't
see
see
anything.
anything.
Okay,
Yes.
okay. Right. That's fine. That's fine. That's good. Okay, thank you for that. You understand shortly where the functions part come
Yes.
in. So yeah, you can see it now, right?
Yes, sir.
Yes, sir.
Okay, flat plate. Okay, so that what you're seeing here is a spreadsheet for a flat plate collector. It's not it's also a solar system type system. I just want to bring up one for you. You can actually see it maybe what it looks like. This one doesn't generate what's the word I'm looking for? Electricity DC. This is for heat purposes, right? So this one is normally for obviously your water heating purposes, right? So I'll paste it just picture here quickly, and you can see what it looks like. Yeah, here we go. So it's these systems. I'm sure you guys are familiar with these ones. So this, right? So this spreadsheet does a few things, right? Yeah, you can select. So obviously solar energy systems are affected by your climate conditions. And what you're seeing over here is your irradiance and your ambient temperature, right? So ambient temperature, this is throughout the year. Can you see this function over here? You see it there? You see it over
Oh,
there? Interesting, right? Now, let me show you something. Yeah, you want to
is
say
this where
something?
the okay? Is this where sorry, sir? Is this where the real life situation comes in?
Yes, this is what I'm trying
Oh,
to show
okay.
you. Yeah.
Yeah.
So what we have here is actually the temperature throughout the year. Obviously this is in the northern hemisphere. Would you notice in these months? Oh, this is throughout the day. Sorry, why am I saying the year? So this is throughout the day. So this is go like that. Eventually goes up and comes down. Likewise with your radiation. Um, I want to see here. So I'm assuming this is my ambient over here. I'm just looking for. That's a so conductivity. So is it this? Is it this? Is it? Oh, it's minuses. Okay. So this is obviously a very cold region. So I just want to plot this quickly. Well, you guys are wondering why I'm showing you this.
Not really for me. It's almost like an eye opener now because sometimes you
Okay.
can't relate where this thing fits into the real world thing.
Yeah. No. Well.
Because I can tell you one thing, sir. Is there's another
Yes.
friend of mine mentioned that he was in Saldanha, and then then area close to Saldanha still was barking off, and they say the engineers was busy calculating
Yes.
the dust. What is the area of the dust? And he asked me how can they determine, and I knew kind of it's got to do with they measuring graphs and trajectories
Yes.
and then they put the
Yes.
math to it. But now I also didn't know exactly, but now it looked like this is
I,
something
I,
different now.
I can tell you what I mean, yeah, it is what you can even do. I'm just trying to put some values, your colleague. Just bear with me here. I'm not seeing it. Okay. I just want to paste these values. So what I was doing is pasting these values here. There we go. I've pasted some values here, right? And what I'm pasting is those values which you saw which is that graph. So I'm going to plot them. Um, and yeah, we can talk about that quickly. And yeah, can you see this? I have a graph here, right? Are you happy with that? Can you see it?
Yes.
Goes like that. That's kind of the same graph. And then on Excel itself, so let's say this is for a particular day, right? What you can actually do, go to Excel, put in a trend line, and go here, more options. So trend line obviously develops an equation for the graph, but you can go to something called polynomial, and you can actually raise the order of the polynomial to a more accurate one. So let me just delete the straight one. Just delete the straight one. So can you see there, that one over there? Can you see this line here? I try to fit the graph. Excel is not the best software to fit lines, but it's definitely one of them. So for a case like this, it might be good enough. Can you see? So I put in a trend line, right? That's basically using a curve fitting type of mathematical thing. I just want to show you the polynomial. I want order, correct. And I go order 5, order 6, perfect. I can do order 6. So I'll delete this one. Okay. So what I just did, I put the equation. Can you guys see it there? Can I just quickly click on it again? Can you see a stipple line over there? Let me just change the color.
I,
Just click
I
on
can't
it.
see anything yet.
Yeah, exactly.
I can't see anything.
It's curved. Can you see my Excel thing, right?
Yes. Yes, I
Yeah.
can. We
Yes.
see.
So watch the line now. Watch the line. It's gonna be a different color. So what I'm saying, let me show you here. If I say order 3, you see this red line, right? Can you see that line, the red one?
No, there's no red line for me.
There's
No,
no
man. How
red
can there be
line,
no
sir.
red line, man? Am I in another book here? Let me just see. Okay, just give me a second. Give me a second. Let me just reshare this guy quickly. Okay. Before we get on our wasting time with this, I thought I'd be done already. Okay, cool. So oh, okay, I see why. Can you guys see this book?
Yes, now we see.
Yeah,
I will
so
see
what I
it.
done was I took the data from the previous thing, right? I pasted it here. Can you see there? I plotted it, which is this line, the blue one. And so what I'm currently doing now, I'm putting an equation or trend line to that blue line, right? Are you guys with me now? So that's the red line I'm talking about. Okay. And now let me just click on the trend line go again. And what you're able to do is you click on him. And obviously this can be extended to a wide variety of applications, right? Let me just click on the trend line and I'm going to make it to the order 6. Now, if I make it the higher the order, the more accurate it will be. Now, watch the red line. It'll curve fit the graph perfectly. Can you guys see it there?
Exactly matches the other curve.
Yeah. Now, this is the beautiful part. So then I click on him. I click on the line again. I can go more options. I go to the end and I say display equation on chart. So right here, see that equation over here?
Uh-huh.
That's the equation of that particular graph. That's what that is. So that what this means is the following. So over on this particular day, the ambient temperature does this. So my X input here was time. So if I put in 15 on this value, like, you know what I mean? 15 over here, 15 by X, 15, 15, 15. I can actually get the temperature at that particular time. In this case, it will be around 10 degrees. Obviously, I can show you easy on Excel, but it'll take me time to type out the equation. So I can type out the equation like something like that, 0.012 multiplied by 15, you know what I'm saying to you, like 15 to the power so and so. I'm not going to do the whole thing, just to take too long. Obviously, I can easily just do it. I type this whole equation in Excel. So what I've just done, what you've seen me do is actually a function over here. Right? So I've curve fitted some data and I made it a function. And this is what this whole thing is actually about, by the way. Because everything is functions, just by the way. So, I mean, I can extend that to a lot of things. Where else? I've got let me just share this one quickly. So if you ever can get data and plot it with two axes, you basically get any equation possible. So like this one over here, just in summary, this one, look at this, like it's the same spreadsheet I showed you before. And here we have the collect efficiency over the day. We've got the solar input. We've got the useful output. By the way, engineers use such type of spreadsheets for all types of applications. And then obviously here, our water comes in at 60 degrees and gets heated up, and then eventually it comes out at 72 and max over here, then eventually drops obviously again as the sun goes. But then again, like I said, we can get an equation for this graph, we can get an equation for this, we can get an equation for anything over here. So that's what I wanted to show you.
That's
Okay.
interesting.
Yeah. So as long as you're able to get some data, you're able to plot an equation, you're able to plot, you can plot, you can get an equation. Yeah. Okay, right. So let's get to the ordinary stuff now. Okay. Right. So just gave you an idea of functions, and obviously this can be extended to a lot of stuff, man. I mean, I can talk on and on how I've used this type of thinking for various things. But anyway, let's move on. So again, we're familiar with the Cartesian plane. I don't need to talk about this. We've got an X and a Y axis, right? That's fine. We all know this. Yeah, the two main definitions which you must know is something called the domain and range.
Yes.
What the domain essentially is, it represents a set of X values for whatever graph or function you're dealing with. The range essentially represents the Y values, right? We'll talk about this as we unpack further. Here they give you a case of what a domain and range is. So here we have a straight line, and what did I want to say to you? In this case, the X values is starting from negative 1.5. It ends at around 3.5, 3 or 3.5. It's 3 over there. I'm talking about this value and that value. So therefore, we say that the range is basically over here. You know, we're saying X negative 1.5 cannot be less than, equal to, greater than, then less than equal to 3. X is element of all the real numbers. That's what that means, and that means all the numbers in between that. And our range in this case will be from that value to that value over there, right? So the lowest point here going right up here. And y is an element of all the lower numbers. That's just pertaining to all the numbers in between. So you would just be in mind that each graph has its own set of domain and range.
Okay.
Yeah, like so you can't say the same thing. You'll see what I mean. For circle looks different, for parabola looks different, for hyperbola it's different. Hyperbola is asymptotes and then the range and domain goes on forever. So you will just be aware. But the idea what domain means, it means x values, range, y values. Okay, yeah, okay, cool. So then we have something called relation and functions. Not really a big deal. I mean, I don't think about this too much. But what this is about is what a relation is. In a relation is basically what they say is showing the mathematical relation between two or more quantities. And it says, this is the key aspect. An equation represents a relation if an x value produces two or more
Excuse me, sir.
y values. Yes.
I think I'm not sure if the other guys can see, but
Yeah, we
there's
can't
not.
see your screen, sir.
I didn't say anything, man. Give me talk too much here. Oh, yeah, okay. Yeah, anyway, so this is the graph I was talking about, the straight line. Can you see it now?
Yes.
Yeah.
Yeah, that part we were on, but after that.
Did it unshare? Interesting. Okay. So here we go. So here's the relation. So an equation represents a relation if each x value produces two or more y values. So I'm going to show you straight what a relation is. And it's fairly easy to determine whether something is a function or relation. Just draw a line segment parallel to the y-axis. If it cuts any graph twice, it's a relation and not a function. Okay. And then for a function is, they say it's a one-on-one type relation where each value only produces one value. Likewise with here, you draw a line parallel to the y-axis. If it cuts it once, it's a function. Fairly easy thing to determine, right? So whatever graph you have, if you draw a line parallel and if it cuts a graph twice, and it will either be a function or a relation. Not a big deal, some boring theory you must know. In the case of dependent and independent variable, this is important. It's very important. Like in the thing which I did, my x-axis was my time, right? So that was my dependent variable, and my y is my independent variable. So these terminologies are important, but nevertheless, so it says a dependent variable is a variable whose value depends on the value of another variable. That would be x, right? Or y. Sorry, y. Then the independent variable is the variable whose value does not depend on the other value. So that's going to be x. So y would be the dependent, y would be independent. Okay, I think that's correct. Yeah, the value of y is dependent on x and x. Yeah, okay, cool. So I'm right. So normally it's quite easy to remember. You think of y equals f of x, because you must input the x value, it affects the y value. So the one that you're inputting is the independent, and the one that you're getting an output for is a dependent value. So I hope that's fairly easy to understand. Some functions I can actually show you. Yeah, but it's yeah. Then this over here, inverse, and essentially saying inverse functions are functions that are the reverse of each other. In other words, one function undoes the effect of the other one. And for us to get a function, let's say for argument's sake, f of x equals x, f minus 1, which denotes function, all we simply do is just swap x and y. I'm going to show you what that looks like. But before I do that, I want to go to this other book of mine, which nicely talks about it's a lot of things which I can show you here. It's linear. I just want to show you functions, domain and range. Where's my inverse? Okay, here we go. Like here. So here they give you some. This book is probably way better than the N5 book. Here it gives a point of something called a function. So here they say a reversible heat pump. I don't know if you guys know what a heat pump is. It's like a heating technology, very efficient one. Is a climate control system that is an air conditioner and a heater in a single device. Operating in one direction, it pumps heat out of the house to provide cooling, and then operates in reverse, and then it pumps heat into the building from the outside, even in cool weather, to provide heating. So you put in X, you get a function, you get a corresponding Y. And when we do the inverse, you're putting the Y and getting the X out. So it's a simple, you know what I'm trying to say? You're just kind of going backwards in what you're doing. So let's quickly look at this example for inverse. It says, excuse me, Betty is traveling to Milan for a fashion show and wants to know what the temperature will be. She's not familiar with the Celsius scales. Obviously, she's coming from America, I guess, or she's going to Europe, starting from America. So to get an idea of how the temperature measurements are related, Betty wants to convert 75 degrees to Celsius, right? So we know the formula over there, C equals 509, F minus 32. And you substitute 75 in, you get 24. So he says, knowing that a comfortable 75 degrees, about 24 degrees Celsius, Betty gets a weather week forecast from figure 2 for Milan and wants to convert all the temperatures, right? So Monday, Tuesday, Wednesday, Thursday. And they say that at first, Betty considers using the formula she has already found to complete the conversion. After all, she knows for her algebra, she can easily solve for F. So what Betty's basically doing, she's got the forecast and she's just kind of converting backwards to F so she can actually see. So for example, to convert 26 degrees to Celsius, you could write that, basically putting 26 in and then getting 79. And then she says, after considering this option for a moment, however, she realizes that solving the equation for each temperature would be awfully tedious. Obviously, that's where we get Excel. Excel can do that a lot for us. She realizes that evaluation is easier than solving. It would be much more convenient to have a different formula, right? One that takes Celsius temperature and outputs Fahrenheit. So you know what I'm saying to you? So instead of having Celsius as the on the other side, on the left-hand side, we want to put in Fahrenheit on the other side. And they're saying the formula for which Betty is searching for corresponds to the idea of a function, which is a function for which the input of the original formula becomes the output of the inverse and the output of the original function becomes the input. Fairly enough to understand, right? So we algebraic manipulated so that the input is the output and the output is the input. And then we talk about that F is -1. So that's what that part is about, basically. Not mentioning too much. And then just quickly showing you what this might look like. Yeah, I would say that the ask for number 1, find the inverse of y equals 3x plus 2. And we don't even need to do this. It's fairly simple. I mean, get to more serious stuff afterwards. We're just flipping the x and the y. As you can see there, the x becomes there, the y becomes there, and we get a new equation. And then afterwards, we write f -1 of x is equal to that. It's clear to everyone.
Okay.
Yeah. The guys there?
Yes, sir.
Fairly straightforward. It's not nothing crazy. You're just swapping the x and the y value and you're just getting a new equation. Okay, so you might see again, maybe you might do it. So there's another one. What you must know with some is continuous or discontinuous. I see this a lot in the question paper. So they're saying if a function or relation produces a graph that can be drawn completely without lifting the pencil, cardinal words without lifting the pencil, then it is a continuous function or relation. There is no interruption or break at any point in the graph. Fairly simple to understand. A graph like this, in ellipse, you start there, you draw a line like that. Continuous, start there, going that way, continuous, going from there to there, continuous. That's continuous graph, fairly easy. But this continuous one, you have to lift the pencil, right? So in this case, you draw a line here, you then lift up your pencil and draw that line there. You know what I'm saying? You draw a line here, lift up the pencil, draw that line here. So that's easy to distinguish. As soon as you're lifting up the pencil, you know it's a discontinuous function. All of these things are useful, especially when you start doing differential equations. It becomes a big deal because, yeah, it really talks to control systems. And a lot of the functions are on and off functions or discontinuous type functions. But anyway, this is a slightly important concept depending where you work. And then coming over here, symmetry, you all know what symmetry is, roughly, right? And if we flip over this graph over the x-axis, it should be exactly the same. So symmetrical of the x, this is symmetrical of the y, that's symmetrical over the point of y equals negative x. So yeah, I think symmetries, we should be smart enough for all of us to figure that out. And then yeah, I think that's about it with those things. That's the interim. And now let's start to unpack the graphs. Okay. And the main operating things here we're gonna use to sketch graphs, to sketch functions and relations. Is that fine to everyone? Are we ready? Are we ready to sketch? Colleagues, are we all ready?
Yes, sir.
Okay,
Yes,
cool.
sir.
Can we all do a straight line? I don't want to waste time on something that we know.
Straight line is fairly fair, I think.
Yeah. Is anyone else uncomfortable with straight line? Or comfortable with straight lines? I don't know waste time on stuff that we know already. If you say yes, I'll do it. If you say no, then I won't do it. Please tell me. Anyone? Can't see any hands, so you must say yes. Can I move on or should I do it? You know what I mean? It's easy.
For me, I'm okay with a straight line, sir.
Okay. Anyone else? Thank you, Richard. I always appreciate. Ashwin, Dalmari, Heinrich, Lori, Liteta, Tanukazi.
I think you
I'm
can
fine, sir.
probably do one or two examples. Sir.
Or straight line, eh? I'm just gonna do one.
Mm.
Okay, because you know time. There's a lot of graphs you must go over. Okay, so I don't mind doing one. So now I'm gonna take that example here and go to my notebook quickly, and then we can start doing one of them. I guess it is kind of important to do it because there's something it's probably a procedure you must always think about whilst you're doing it. Richard, so long, you can also think about what is critical. So we can actually solve what is also critical. Okay, so here we go. The first thing I want to say, each function will have its own equation, right? For straight line, there are three forms. X plus by plus c equals 0, y equals mx plus c, the gradient point form y minus y1 x, the intercept form x over a, y plus b equals 1, and then you also have, what is this? This looks like a gradient. This is something called a 2-point form, which I'm not familiar. So there's many ways to draw a straight line given whatever you have, right? So I'm just making you aware. However, the following is always holding water. And the following is this. Where's my pen? So, okay, so yeah. So why? I just wanna write this for you. I'm just check a few things that open your mind now. But let me just ask this question. So we have a line like this, right? That's my Cartesian plane. I'm gonna sketch this here. So you tell me this, is this a positive or negative graph?
Positive.
Why is it positive?
Positive.
You know why it's positive?
The gradient is positive.
That is fine. Okay, gradient is positive. Why is the gradient positive? Okay, do you agree with me? That's positive here and that's positive there, right? And that's negative there, it's negative there. Are we all happy with this? That's x and that's y, right?
Yeah.
Positive times positive is what? Positive, right? Negative times negative is what?
Negative. Positive.
Positive. Negative times negative is positive. You see there? If I draw a line like this.
Oh, that's a nice way to remember it also.
Yes, if you draw a line like this, that's negative times positive is negative. Negative times positive is what? It's negative.
Negative.
To do the axes, to do the signs there. That's what we are determining, because technically this can also be positive if you're looking at it from this way. You know what I mean? Going up that way. So just making you aware where it comes from. All right, so how do we begin this? Again, we can tackle it in many forms here. I think what is key to understand from these formulas, and I'll start with the most fundamental one, is y equals mx plus c. Very powerful formula. I use it several times. I mean, especially for calibration purposes with thermocouples, we use these ones. There's a lot of, not everything around it, but a lot of things has a linear relationship. And you'll be lucky to get a linear relationship. That's what you always want, because normally things are never linear. Nevertheless, so what are the following stuff? I think we all know X and Y are the intercepts, right? Is it fine?
Yes.
Yeah.
Yes.
In fact, no. Let me say this. So in this case, C is the y-intercept. I don't know how to say it. Yeah, C is the y-intercept. The X and the Y are coordinates on the graph. Coordinate on graph, right? And then the M is something called the gradient, right? Which obviously tells you it's going to be a positive or a negative, right? So here they're asking, determine the equation of a straight line passing through points -2, -4, and 1 and 3. Okay. So I believe you all know the gradient formula. Change in Y over change in X. Sorry. It's actually like a derivative. I might not know that. And M is equal to, so that's going to be 3 minus -4, right? I don't know if you guys know what this looks like, by the way. It looks similar to this. So I'm just checking. Anyway, this is not the same though, but this is what I'm doing. So it's y2 minus y1, x2 minus. We also use a straight line for interpolation, by the way. I don't know if you guys are familiar with that. So it's -4, -3, right? And then x is going to be 1 minus -2. What is key, you can subtract the values, like if this is -4, you must say -3 and then -2 -1. You can do it the other way around by saying 3 minus -4 and 1 minus 2, but you must just make sure you uniform as you do this over here. So if you solve this guy there, you should get a gradient of, I believe, what do you get there? Is it -7, eh?
Yes.
Over 3. Okay. So that's a negative gradient. So once you have that, I don't know what you said this. So once you have that, you have this part, right? So now you need to get the equations. Obviously, you can actually just substitute values into this thing here. So let's quickly see what this is. So y equals, I want to prove to you something. Mx plus c, our m is given as -7 over 3x plus c. So what we're finding is c here. There is steps on how to remember this, but it's hard to articulate that properly, given that I have such a short time. Nevertheless, all we have to do is substitute either one of those points. So either one of these points can come into this graph, and you'll find out you'll get the same c value. So let's take the first one. So we're going to say sub -2 and -4. Okay. Sub -2 and -4. So that is a y value, right? Okay, -4 comes in here. That's -7 over 3. We put in -2, and now we got to find c. Can anyone get a c for me quickly? Should get the same values either or, yeah.
3.
I believe it's 2 over 3. Quickly calculate for me. What do you see? Okay. Yes, you calculate.
3.781.
3.781. Isn't there? I can't just get in fractional form there instead of. So it's -4 basically plus 14/3, no? 2/3, yeah. 2/3 or 0.6667, something like that. I'm just taking this over to that side.
Yes.
Yeah, I believe everyone can do that. That's quite easy. Am I right?
Yeah, that's fine.
Yeah, so y will be -7/3 plus 2/3. And that's my equation. So there's an x here. Okay. Or we can write it f of x equals -7/3x plus 2/3. Everyone get that?
Yes, sir. And it's,
Perfect.
it's and it's the C is always where it cuts the y-axis.
I'm gonna get to that now. Yeah, don't worry, don't worry.
Okay.
I'm gonna get to that now. So, if you want to plot this graph, I want to show you something. So let me just get my Casio open. Okay. And I want you to remember this procedure for all graphs, just by the way. Let me share my calculator. So, and when I say all graphs, I mean all graphs, right? So if you want to plot this graph, can you guys see my calculator? Should appear.
Yes.
Okay.
Yes, sir.
First step you do, thing we all can do together, press mode, and you find table. You calculate if you have a Casio. I'm hoping you have a Casio. If not, you got a divorce, whatever you have, and get a new one. So then mode, you find table. It could be number 2 for some of you guys, no? We go 7. That's fine. Who's with me?
Okay.
Okay, and you type in your equation. -7, 3, alpha x over there, right? Plus 2/3. I'll just give it a minute here. We're all on the same page. Dalmarie, Tanukazi. Who else is there? Yeah, Lori.
I must first divorce. I don't have a case.
You see, this is the problem. The loyalty. Yeah. Yeah. Let's. I'm gonna explain. I'm explaining to what we're doing. Okay, done? Can we move?
Yes, sir.
Yes, sir.
Okay, perfect. Right. So once that is done, you press equal and say g of x is 0. And the reason why you put this 0 is that there's no other graph. So if you had 2 graphs, you could have put another graph in here, right? Maybe you want to find points of intersection. Then you come to start. Now start is basically the x value you're going to input. So let's choose a wide range, or let's say from -3. We're going to input from -3, and we're going to end at number 3. I hope that's clear to everyone. Like understanding what it means, no? And once you do that, you say step 1. That means it's in increments of 1 unit. So -3, -2, -1, 0. You can change the increment depending on the resolution of the graph you're dealing with. Just letting you know. And once you're done, you press equal, and you get a table of a lot of points there. So this table over here will be the x is your x input, what you've inputted, and that'll be your y input over there. I hope that's obvious to everyone, right? So y, and then what is it? Sorry, x and then y. So this over here, as you input that into the equation, you're going to get 7.666. Yeah, you get 5.33. If you input -1, you get 3. Okay. Is everyone with me on how that works, or what I just did there now? Did you guys get that?
Yes, sir.
Okay, cool. So once you have your points, let me just quickly share. Let me share. Yeah. So can someone just read the y values for me quickly, man? If you don't mind. Yeah. So what I'm doing, I'm, yeah,
7.66.
yes, again.
7.66.
Perfect. Next one.
5.33.
Yes. Continue.
And then it's 3.
Yes,
And then for 0 is 0.66.
that's correct. If you input 0 here, we should get that. Yes. 1.
And then it's negative 1.66.
Yeah.
And then it's negative 4.
Clean.
And then it's negative 6.33.
Negative 4 clean, huh? Just negative
Yeah.
4.
Yes.
Okay. All right. So all that was is inputting negative 3 and getting a y value. I hope you understand what's happening within the calculator space. So instead of us doing this, obviously you can do this easy on Excel as well. Then what you do is obviously you want to put plot points. So you draw your X and Y Cartesian plane, right? Maybe let me be a bit more dramatic here. Okay. Let's bring my ruler. Hey. So I'll make it 0 over here. Drawing functions by hand is very 90s. I don't know why it's in the curriculum. Drawing a function should be done on a computer. Nah, I'll be honest with you. It's really something which we should move past on now. Especially at the tertiary level. I'll make this 90 degrees. Where's my 90? Why can't I make it 90? I'm using my laptop mouse here. I clicked on it. Okay. Let me just change to my other mouse quickly. Pause. Second. Yeah. I'm sorry about that. Okay, and then we can just make a straight line here, just like that. Okay. Cool. So then we make a straight line over here. Perfect. Say goodbye to my ruler.
Just fix the screen also, sir, please.
Say again?
The screen is off again.
Ah, man. Yeah. Someone's multi is working. Multi-strong, Sangoma is working overtime. Let's quickly see ruler Y. Okay, thank you, ruler X and Y. And so what I mean is that at negative 3, we have 7.66, right? Give or take. I hope you guys are with me here now. 7.66.
Yes.
I'm being very particular here. I didn't think I'll end up doing this. Negative 2 is around here somewhere. That's around 5.33. Negative 1 is around here. That's 0, obviously. Negative 1 is around 3, which should be somewhere here. Obviously, this is not to scale, so you must bear with me. And then at 0, we have x is going to be 0, negative 1, negative 3. Oh, this is going to be 0.66 something here, no? It should be here somewhere. 0.667. That's before, or just by 1, before 1. Like that. 2, 3, 4. Obviously, this is am I going the wrong way around? No, it's
So
right.
shouldn't the 0.667 be on the y-axis?
Yeah, that's what I'm not thinking now. I was like, yeah. Delete. Yeah, there we go. So that's x is 0. That's 0.067. Thank you for that. I was now going to say. Obviously, you can understand where it's roughly about. And 0 and 1 and minus 1.66. Obviously, that's there somewhere, right? This is going to be a 2, which is somewhere here. That's going to be the next value. It's negative 4. And then 3, let's say it's somewhere around here. It's negative 6.33. Okay, somewhere around there. Let's get my ruler out. Make an approximate. Also, the ruler's going to be spot on. But I hope you guys are following at least.
Yeah, it's perfect. Yeah.
Yeah, great.
That's it.
Yeah, and it's the same kind of procedure. There we go. Amen.
Yeah, it's a pretty nice one.
Yeah. We thank the Lord for technology. But yeah, that's me drawing a straight line there, right? Is that fine with everyone, right? That's just covering the fundamentals. And another way there's many ways of doing this, man. So you can use this formula, you can use that formula, but it basically generates the same thing. Are you guys with me? Or roughly the same?
So
Yeah. Yeah, it's just different ways of yeah, I don't know, man. I don't know how much things I should focus on with a straight line. Okay. So can we move on, or are you happy with this? So we can move on to the next graph. Is there any other questions? Please ask, it's our last session, basically. So let me try this one. Let me show you this form quickly. I'm going to just illustrate this form and then we're going to move on. Colleagues, are you still there?
I'm still here, sir.
Okay.
so yeah, so
So I'm going to show you one more form. There's a lot of graphs to go through. You understand why and I'm trying to make sure you guys get the full experience. Yeah, we've talked about the first form, and there's another form called this intercept form. So if you do see it, don't get shocked. But they're saying that x over a plus y over b equals 1, and they're saying that x and y intercepts are given by a and b. So if I were to use the graph you've just used, I said a and b are the intercepts, right? I'm trying to figure out something here. Okay, let me use this example here. But I mean, we need 1 point on the graph. Okay. So let me just use this example here. Example 4.5. I'm just going to demonstrate to you what it could look like. I've seen it in 1 or 2 papers I went through. But what you have is you have one intercept of 0.5 and you have the x-intercept at 0.2. So what's key here, and I want to show you what the one we just did now, is to use that equation, we must make the one value 0 to get the other value, and the x value and get the y value to make the other one 0. So it looks something like this. That's what's key here. And then determine the equation straight line expression on gradient form. So once you do that, you basically plug in those intercepts. X was 2, y was 5, and you make it equal to 1. What they then do, they look for the common denominator, right, of the two, and that's obviously going to be 10. Like I rather prefer doing this way. I'll show you now. Now I'll show you with the previous one as well. Just trying to get that right. But anyway, so this one, like I said to you, we made it equal to 0. We found the point, so we have the point. It's x plus 5, x plus, that's going to be 2, and so 5 equals 1. Instead of find the lowest common denominator, I said 2 times 5, like that, something like that. You know that technique, 5 times x plus 2y equals 1, something like this. Quite simple. You times of 2 times 5 on the other side, you have 5x plus 2y equals 10. And then obviously we can just rearrange it into standard form. You just take, say, 2y equals minus 5x plus 10, and obviously divide both sides by 2. You have minus 5 over 2x plus 10 over 2, which is 5. So that's one way. Like another way, but like I said over here, we can do exactly the same thing with this one over here, right? And for this one, we have to make x0, and then you get that is y. You make y0, and then you can get an x. And then once you have those values, you can actually use this form. But if you ever get a equation typically looks like this, so just be aware where to put what. Yeah, it's not that tough. It's not that tough though. But I don't want to do too much of the linear stuff. You know? Okay, let's move on, colleagues. Let's move on. So next function is going to be circle, from what I see here. And I think I should have mentioned, and be cognizant of the fact of each thing, right? On the straight line, you probably have to make notes. The graph is a function. We draw a line, there's not 2 points, it's continuous, you don't lift up the pencil, it's symmetrical, and obviously the domain and ranges you can also look at. And then we just look at the circle. Circle, you draw a line, cuts at 2 points, therefore it's a relation, right? So therefore it's going to have one and more x value for y value. The graph is continuous. Obviously it is symmetrical with the x and the y axis. And that's the standard form of the equation. Your domain is fairly simple, and your range, and obviously it's limited by both the radiuses of this. This equation is very powerful. A lot of things are shafts or circle in the mechanical engineering domain, and therefore it's a very, very usable formula. But anyway, let's quickly see how we sketch a graph. And the standard form for the graph is x squared plus y squared equals r squared, right? And in this case, the origin is always the center for this type of graph, just for the syllabus. So let me quickly illustrate to you some examples of graph. You know, I'd like for you guys to solve some stuff, but the nature of this chapter is to show you now. How do we do it? It's really easy. Okay, so how do you sketch those graphs? Number one, x squared plus y squared equals 36. The first thing you want to do, the radius part, which is the r, you want to make it into a square, right? So that's going to be 6 squared. You guys agree with me?
Yes, sir.
Yeah. And the way you typically want to do this, just like standard graphs, to find x, you make y0. Are you guys familiar with this? To find y, you make x0. This is a very powerful concept here. So let me quickly do that. Find y, find x, y must be 0. That means it will be x squared plus 0 equals 6 squared. We have x squared is essentially 6 squared, right? Well, that's 36 anyway. And you would just say x root 6 squared, you get 6, but obviously plus minus 6. Is it fine to everyone? So we know x coordinates is plus minus. Say find y. Make x0 exactly the same thing, but 0 plus y squared equals 6 squared. Y root 6 squared, y will be plus minus 6. Easy, all from the center. Again, let's quickly now format my background here. Look at grid lines. There we go. Okay, just move that. Just gonna draw a line here. Also, I'm doing my Cartesian plane here. By the way, if you're wondering what I'm using here, I'm using something called a graphics tablet. I don't know if you guys are familiar with that. And the software I'm using to write is Microsoft OneNote, if you are interested.
Oh.
Yes, sorry.
No. I just said okay.
Okay, I see. Yeah. And then obviously here we can just say maybe 1, 2, 3, 4, 5, 6. Let's say 6 is here, -6 is there. I'm approximating 1, 2, 3, 4, 5, 6. 6 is there. 1, 2, 3, 4. Let's say 6 is there. And all what you basically do is now gonna sketch a circle, right? And these will be the radius of the circle. I'm not sure if I have a straight line type of thing here. Okay, no, I don't have no. Do I have it? No, it's not gonna work out. I'm sure there is just a perfectly straight line thing here. Let me just check here. Anyway, so all you have to basically do is you wanna, you know what I mean? Go like that. Like that. You just obviously want to make sure you're using a compass, you know what I mean? With the origin being the center over here, and just draw a nice circle for you. And that'll be a perfect circle. And that'll be 6 over here, -6. Okay, that's it. That's it. There's nothing more, nothing less. I can't even, there's no other tricks. That's basically it. And like I said to you, with this one, the domain is these values. So it'll be -6, less than, greater than, -6 to +6. The range will have something similar as well. So that's the domain. All the values from here, X is an element of all the raw numbers, right? I don't know if you guys are familiar with this concept, you know. Okay, so that's a circle. Are you all cool with that? Was it easy to understand?
On my
Any
side,
questions? Yeah, it's really not much to say, man. I don't know what to say. It's just straightforward. Would have taught you in grade 1, you know what I mean? While you're in the womb, sorry, I speak under correction. So then the next one, we have your semicircle, nearly the same as a straight line. However, there's a root formula. And exactly the same concept as the previous one. So I don't think I'm gonna spend time doing this, but obviously you make the x0, y0, depending on what's happening. And if you want to get, yeah, that's basically it. And obviously they explain to you a few things regarding that. Okay, this might be a new graph. This is called an ellipse. Right, this is, let me quickly see here. Reads. You probably think this is a useless graph, but because I'm teaching in the maritime department, I want to show you something quickly. Just let me know if you can see this book what's going to come up. So this shape is one of the, can you guys see a book called Naval Architecture? Yeah.
yes, sir.
So,
I want to show you just something here. So that shape is an approximated shape of a ship. And this is some of the coefficients they use for that shape. This is one of the form coefficients. So if you're into NAVARC, it's a nice book for you. Our department teaches the subject. Oh, here's another idea of an area, which you must find an area under curve, which we actually use integration, by the way. This just talks about if something is stable or not this one in particular, but yeah. Here's a drought and all of that. I'm looking for this particular one. I don't teach NAVARC, so I'm looking for an ellipse, man. Let's see the GZ stuff. But again, yeah, not that. But it's a shape which they use for approximating I think it's the water plane area or something like that. That's what they call it. So it's a very important shape, especially in this type of work. It's bending and shear, bending and shear force. You guys have done that on beams. It was approximated the ship to be a beam. Just looking at that, there's resistance. Ach, can't really see it here for some reason. I'm going through it too fast. But anyway, that's important shape, the ellipse. Let me just move back. So, what are the ellipse? That's your form, x squared over a squared plus y squared over b squared equals 1. Looks quite similar to that other form you're talking about. And it's quite simple. X, a squared and b squared represents the intercepts. Can you see that? Negative a and a, b, and then negative b. Can you guys see that there? Quite straightforward. So let me quickly do an example for you that I think I want you to draw an ellipse for me. No? So quickly let's get that. Let's get through this. Let me share my OneNote and we can begin. So you first make the x0, then the y0, that kind of thing. Let me just quickly do it. Okay, it's supposed to be circle. Just want to place this here. You'll see it now. Okay, here we go. And this is circle. And I think what's important, or I should have mentioned, that you always want to get something into the standard form, no? Of whatever's been given. So the standard form for the ellipse, like I said just now, I believe it's on your formula sheet, so you have to really bear with me. So it's x squared plus y squared over a squared plus b squared equals 1. I'm surprised where these formulas come from. So let's quickly see. How do we get it? So the first step is you want to get this into general form. Okay, so let's do the first one, number 1. So you have 27y squared minus 27 equals minus 3x squared. So you're going to bring the general form. So you carry over the 3 on the other side. You have plus 27y squared. I'm following that. Obviously, this will become 27. You probably want to divide out by 27 on either side, I think. It'll be a smart move to do. It'll be 3x squared divided by 27. Okay. Plus 27y squared divided by 27 and 27 divided by 27. You want to get a 1 here, basically. Here you can get you're going to get x squared over 9, I believe, which will be an intercept, as you can see. Plus, you're going to get y squared over 1, and here you're going to get 1. So there we have our standard form for our ellipse. But of course, you must remember the values at the bottom are squared. And so therefore, we just say 3 squared plus y squared. Now they're typically always a square over 1. And right there, you have your intercepts. No? And it's easy to remember how the graph will look because this is the y value, that's the x values on that side. Okay, so once you have that down, you can obviously draw a line. That's going to be positive 1, negative 1. Obviously, you can do the maths here, but it's fairly obvious. You make x 0, no, to get y, to find y. I'm just going to show you. It'll be 0 squared over 3 squared plus y squared over 1 equals 1. That'll be 0. You're left with y squared equals 1. Obviously, square rooting plus minus 1. Are you guys with me? You know what I mean? You do the same thing on this side, you get plus minus 3. All right? That's 3 plus negative 3. Then you just get your ellipse, just like that. You know what ellipse looks like? Nearly a circle. You know? And that's in. One is called a minor and one is called a major axis. Done. Nothing more, nothing less. That's your ellipse. So let me quickly see if I can find something for you. I just want to check the book quickly. Yeah, I don't know if you have enough time here, but I want to get to. Let me find just. Yeah, this looks like one, isn't it? Okay, let's quickly see here. I want to give you one, but I've got some questions here, which I want all of us to engage on. Is this a function or relation? Let's start there.
Relation.
Relation.
Exactly, the relation, right? We know that thing. Is it continuous or discontinuous?
Continuous.
Continuous.
Perfect. Yeah, that means you guys are geniuses. And then obviously our domain is the x values, and that'll be -3, x less than greater than x less than greater than 3. It's a positive 3, sorry, colleagues. X is the element of all the real numbers. And the range will obviously be -1 less than greater than. Does everyone understand what I mean here? No? All the
Yes,
values from here till here.
So,
Okay. I believe that's correct.
that is good.
Yeah. And then for you, I love you guys. I have one for you to do. Okay, look there. Few marks there. No? Let me give you guys 5 minutes. You guys can probably do it in a minute. Okay, go for it. 5 minutes. You guys winning?
I'm done, sir.
I'm talking, but I was muted. What is your question, Tamari?
I said I'm done.
I know, but your equation, yes, I heard that you're done, yeah. What's your standard equation for the ellipse?
X squared over 5 squared plus y squared over 4 squared equals 1.
Like this. Okay. Because one like that, right?
Yes.
Colleagues, we all get that?
Yes, sir.
Yes, sir.
Okay, great stuff. Okay, I don't think I can do the rest, but I mean, you can fairly see how simple it is, no? Yeah. Another thing I was just reminding myself of the reason why an ellipse is important is obviously also the orbit of planets. So obviously they have the, I think I can paste it here. Yeah, it's as it moves around the sun. No, I don't know how they approximate these distances, but I guess that's another important reason why the ellipse is an important shape. Okay, so let's try to move on. Let me see. Time is catching up. I want to show you this interesting thing as well while we're here, where functions can be viewed or where they come from. So imagine this conic section over here. And if you slice the top of the cone there, right? I'm sure you guys know what a cone is. I know real men don't eat ice cream cones, but anyway. You cut it from the top there, and you slice it like that, that'll be a circle. Slice it at a particular angle, that's an ellipse. You cut that piece at a certain angle, that's a parabola. If you cut it right down, you get something called hyperbola. I'm not sure if you guys have ever seen this before. So they call this the mother of all shapes, conic section, of all functions, so to say. Yeah. Right, but there's many things where this comes into play. Oh yeah, let me show you this one. Spend too much time on Pinterest. I just want to show you this quickly. I'm not sure how true this is, but this is something called the shape is called a hyperbolic paraboloid. Hyperbolic paraboloid. And the idea was, I think, when they're developing this thing, it was something about fitting it into a sphere, man. But one of the uses they did was, I'll show you now. You see what I mean? It's a function. Here we go. So it's a Pringle, right? It's a hyperbolic paraboloid. That's what the function looks like. Yeah, and yeah, it's crazy, and it's like it's an optimal type of shape. I don't know, it's can't call the history, but I know they like an optimization, and on the chips and on the actual sphere, not the sphere, the cylinder, and how much they can fit in, and yeah, so I don't know exactly what's clapping here, but there was something I just can't remember the full thing, but I remember it now as I talk to you. So yeah, that's the actual shape for Pringle. Like that's the actual formula right there in front of your face.
The Pringle.
Oh my word.
Yeah, you know, I'm being genuine. That's the thing. Go check it out. Yeah, I can see the took on plot on a certain domain. Yeah, but that's there was other formula, but it's fine. I'm not going to show you that one. Let's move on. But that's a legit actual shape. It's I just can't remember the exact thing with it. Anyway, let's move on. Let's go back to the book. Yeah. And then come over here. Let's see now. Let me know if you can see the book. Okay. Right. Can you guys see my PDF?
Yes, sir.
Yeah. So anyway, also wanted to show you Fortunately for you guys don't have to derive the formula, but this is what the whole derivation looks like. So yeah, that's the whole derivation for it. So it's algebraically extensive, but you definitely can follow the reasoning behind it, and it's the talks to the distance formula coming into play, blah 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 blah. But if you ever wondered, that's where it comes from, and each shape had its own story like this. Okay, so now we did what did we do now? We just did the circle, now the ellipse. And there is also something called the hyperbola next, which I'm going to go over quickly. Probably going to skip the exponential. I might even skip one of these ones. But anyway, the way you say it is hyperbola, as I say here. I've never used this in a professional capacity. Yeah. Yeah, so that's your general form. Yx equals k. What is key of this graph is discontinuous. It's a function. And there's also something called asymptotes, which is essentially the x and y axis. In matric, this is a bit more, this is the thing that this is the grade 10 type of thing. So the saying is asymptotic, meaning none of the graphs touch the axis. They approach, but they don't actually, that's what I'm looking for. They don't touch. So that's a standard form over there. So a positive graph will look like that one. Again, positive times positive, positive times positive, negative times positive gives you a negative graph. So you know whether you're a positive or negative graph. Again, the only difference is the key here is that in the domain, you have this part here, x cannot be equal to 0, and y cannot be equal to 0, which talks about the asymptote. These change if the graph is cutting on the axis, but I don't think for this case it does. Again, then there's a non-rectangular hyperboloid. Oh, this is quite similar to the Pringle shape I showed you. And they look like this. And again, it's a relation, it's discontinuous. You lift up the pencil, that's that form. And again, it's you apply the same concepts in terms of what's the word I'm looking for? They're making the x0 to get the y, get the y making the x. So yeah, you can see over here, same type of thing, right? Nothing crazy. And what is key, what I ask you is relational or functional, state the domain, stuff like that. There's exponential. Obviously, this is a very important graph. You see this a lot. A lot of things have this relationship. On this side over here, on the left hand side is men. Men over time gets better, right? That's men. Women over time it drop. Age like wine, age like milk.
Am I the only woman here now?
Yeah, and Tanukaze, I believe, is also there.
And she's quiet.
No, she's just probably not listening to my nonsense. But yeah, but obviously there's many things. A voltage increases through a capacitor, or voltage drops through a capacitor. I'll show you one exponential graph. Again, all these things are fairly easy, man. You just know the formulas. I just want to show you the voltage drop in a battery. I can remember, right? That's the amount of capacity. Like, I just can't remember, man. Equation. Yeah, I'm gonna show you an equation. See equation. So like over time, how the battery basically loses charge, man. I'm just not finding the voltage drop. Why am I not? Yeah, during the as it discharge, how it loses voltage, man. It's a formula for it, man. I can see the graph here. I just want to see Homer. The depth of discharge is that's what it's called again. Just want to quickly see. I think I can find one. And again, this came into play for me when we were looking at solar PV systems, man. You know, when you're looking at the days of autonomy of how long the battery must last. But I just can't get to this. There's an equation, man, you know? Yeah. That's fine. It's fine. It's fine. There's an actual equation, but I'll just show you the graph while I'm here. I don't always take my whole time and not show you.
Where are you working, sir?
Me, I
People
work,
asking.
you know, I work at CPT. You know, you can ask. You can ask.
Okay.
Yeah, yeah. And where do you work?
I want to say
You won't say.
no.
Why not?
We're not a very famous company, so I'm not going to say.
No, it's Varela. It's not about that. Famous companies don't mean anything, man. You know, it's the people who make the companies good. But
We're being bad mothers, so I might keep quiet.
understood. So this is the graph I'm talking about, and that equation with this relationship over time is an exponential one. It's just that I can't find that particular, you know what I mean, the equation for this. But there's a standard form. Maybe I should just find it, man. Yeah. So that's the equation. That's the graph I'm looking at. So again, exponential. Okay, let me just show you maybe on Bird also. It's fine. I'll show you some other stuff where these functions come into play. But the maths is fairly easy also. I think maybe it's a good thing the left is for last. I don't know. Yeah.
Is this a similar they call exponential decay?
Yes, 100%. You got it. You took it out my mouth. Yeah, that's exactly what it is. Exponential decay. Now I'm gonna show you some stock relationships now. That's exactly what it is. Yeah, I'm gonna show you some now. There you go. I'm gonna paste it. Print screen quickly. Where this is very common relationships. Like exponential is something that one must kind of know as an engineer. I don't know if you guys are all in engineering, but here's linear expansion. This is basically, you know, if you heat up a material, metal will expand. There is electrical resistance, also exponential depending on the material. It's not always linear. There's tension in belts. So you see it in mechanos. There's Newton's law of cooling, biological growth, discharge of a capacitor. Obviously, that looks like that. Atmospheric pressure is not linear. It's exponential, as you can see. Decay of current in inductive circuit, growth of current in a capacitive circuit. Very, very important type of thing. Again, even with the COVID pandemic, they are using functions in relationships like this, predict and so on. Just thought I'll mention that there. So the exponential, let me just try and do one. I believe you all know what the exponential is. Do we all know? It's not difficult to. Should I do an exponential graph for you? Or you guys are right? Super easy. Should I do one for you? Sorry?
This one.
Okay. I'll do one for you now. Just give me a second. It's really not that deep. I promise you. I just wanna.
How many marks does graph take of them in the paper?
I can check for you quickly. Do you check the study guide on the group? Is like I think they put up some, but it's easy marks. I don't think it's difficult, colleagues. I don't know what you guys think.
Because
It's
the
really
past question papers that I've got is like 10 marks.
Yeah, there we go. It's not much, man. I'm gonna show you the.
So that's it.
It's not a lot, man. It's really not a lot. Let me just quickly go to. Just wanna see. It's under the study guide. If you go to the study guide, so it says weight values like 12%.
I don't have my study guide with me now.
Yeah, I'm gonna send it now.
I'll check tomorrow. I did
gonna send
print
it
all
now.
my stuff.
Yeah, you'll see it now. Yeah. So it's like 12% of 100. Integration is 20, limits is 20, sketching graphs is 10. Okay, maybe this is a bit old, but it should be around, it's around 10, yeah. So anyway, there you go. So how do we sketch this? Fairly easy. I'm going to do number 2 quickly. Y equals 3 e to the power x. Only thing I was mentioning, if this part is negative, the graph goes that way, right? And if it's positive, just like that, it goes like that. Yeah, that's basically it. How do we do this? To find x, we make y 0. Let's quickly do that. That's 0. That's 3 e to the power what? X, no? If I divide this by 3, 0 divided by 3 will give me what? 0, right? So that doesn't really work out. So the 0, that's e to the power. So my x is 0 in this case, it seems. Is that correct? I do think so, yes. Then to find what's it again? Y, no? Make x 0. We do the same. Y equals 3 e to the power 0. Anything to the power 0 is 1. Right? That becomes 3. Then we have a line like this. So that means the only coordinate where it cuts is 0 and 3, which is going to be over here somewhere. And all we do is just draw a line like this. Going up like that. Right? And there you go. That's it.
It's not touching the x.
It doesn't touch. It doesn't touch it. Doesn't touch it all. Doesn't touch. Doesn't. The only intercept it has is that value over there. Are you with me? And that's always typically the case, unless there's a shift. So it's always like that. You'll cut once. And again, I don't know. And so then after that, this is so much. Okay. I think after that, let's look at, here we have the log graph, which is actually the inverse graph of the exponential graph. A lot of things I can talk about the log graph, pH level, log graph, the pH decibels, also uses log function. Yeah, a lot of things.
Is it
Anyway.
safe to say the exponential graph cuts on the y-axis and the log graph cuts on the x-axis?
We could say that, yeah, for sure. Yeah, it's a good way of looking at it. Yes, that's correct. Yeah, it was like the kind of the inverse of each other. Yeah. Yeah, that would be a good way. I never thought about like that. Yes. Oh, this graph has an inverse function, and the inverse function is, they are the inverse functions of each other, by the way. I'm not sure why they didn't mention that. But anyway, yeah, that's that. You can do a similar principle here, I guess. I don't know if you guys know the type of logs in the calculators, but yeah, that's that. Okay, hopefully this doesn't come in. And then yeah, this is parabola. You guys have experience with parabolas?
Yes.
Yes or no?
Yes.
Yes, sir.
Everyone should have experience, right? I mean, we all understand how the parabola works. Yes or no? Anyone?
Yes, I do.
Yeah, is there anything I should maybe highlight here? Anyone?
I almost think this parabola is second most important to the exponential.
Why do you think that?
No, I just think so. It looked like because it's always a critical thing to calculate and everything.
Yeah, I mean, but this is again, I don't know if you all can do this. I can go over one if you want, but I mean, it's also fairly easy taking, factorizing for the intercepts. Yeah, this is like grade 10 essentially, I don't know if it's worth going over. Let me just quickly look at the paper and see if I can maybe just look at what a paper looks like. If I have a paper on my phone here, just to quickly see, man. Where's this maths? Okay, I'm just looking at a paper here quickly. Just give me a second. Maybe we can see what I think, okay, colleagues, I think what we should do, let's do a past paper question to end off, right? Is that fine? Is that fine with everyone?
I've got the August 2025 paper.
Good, sir.
Yeah, you can send it in the group.
Okay.
Yeah, and then we
Do
can
it
solve it.
quickly.
Yeah, and I'll send it to my laptop. And then we can end off with that. I mean, I think, yeah, you guys will just navigate the rest, maybe, but it's not tough, man. It's not tough, I promise you.
I add it in the chat.
Yeah, okay, I'm waiting. I haven't received anything yet. I did send the syllabus thing there so you can see roughly.
Bear with me, my PC is a bit slow.
Okay, okay.
I did send some question papers in our
I did see, yeah.
WhatsApp group. Yes, if you guys want more, you can just say.
Yeah. Yeah, I see them, yeah, I see them. And I see there's one function question is 20 marks. You send it?
I don't know what's happening here now. It doesn't want to copy and I can't access the file.
Let me just quickly see. Maybe I can download it. I believe you guys know where to get the papers from, right? Let's see. In four math. Okay. 2025, eh? Yeah, got it. Yeah. Just send it to my email quickly. Nearly there, guys. Nearly there. And then, okay, it's coming up. But I promise you, I don't think it's that. I mean, with all respect to this thing, it seems awfully easy. It's the functions part at least. Just got to go over a few stuff. Okay. Okay, I'm gonna bring it up now. I believe it's sent. Okay, where are you? Okay. Just waiting still. Yeah, did you manage already?
No, I can open the PDF, but I can't access it from my, because I'm about to put it in the chat.
That's fine. I'm gonna open it now. Okay, just synced. Yeah. Okay, yeah, here we go. So this is obviously August paper, guys. It's coming up. And let's start to see if we can solve it. 10 marks only. So just quickly do that. Let me know if you can see it, eh? You guys see it?
Not yet.
No.
Yeah, there we go. Yeah?
No.
Nothing. What am I sharing? My book still, no?
You're still sharing the book, yes.
Okay, yeah, that's right. Let's open him up. There's this now. Okay, so there we go. All right. See that? What's so funny? Tell me you're laughing. Me trying to figure out why you're laughing. Are you all right?
No.
What's wrong? Yes. Not saying anything. Okay. So there we go. So that's the paper there, right? So the first question, the one has to draw log 2x. Do you think you're able to do that? Anyone? You can just say yes or no.
That's why I was asking how many bucks is this?
Yeah,
Because I
but
don't think
it's fairly easy, man. I mean, so if you go to your calculator, again, it's really not that tough. You can
but they were
actually score,
using the Casio one now because
obviously, yeah.
I
Must
found my
upgrade.
son's one. No, I found my son's one, so it's fine.
Okay, good. You must upgrade me.
We just send that model, that Casio model through as well.
Don't worry, I'll send it to you. So can you see my calculator there?
Is Casio the best option for
100%.
Okay.
I'm still old school. I have a Sharp.
That's the problem. That's the problem. That's the issue. You must move on.
My Sharp is also working.
That's the problem.
Up until
It's working up until here.
Loyalty, yeah? Yeah. Okay, so here's y equals. You can say log 2 alpha x. I know some shops can do it. Can you see there? What I just did? I just typed in the equation. Is it fine to everyone? F of x represents y. Got that now?
Yes.
Equal,
Yes.
g of x again is 0. Start, we can just say -5 to 5. Step 1 equal, and then there we have errors in the negative. And then eventually we're going to have some plotting points from over here. So I think we're going to start at 1 and 0. Yeah, and another reason why it's errors there, because it's not cutting the axis, man. You know what I mean? So let's see if I can plot. I just can't actually get. Okay, let me just. So that's the way. Let me just put the graph quickly for you. Yeah, I'm gonna just sketch, and I wanna just quickly keep my calculator next to me. So yeah, that's how you're gonna probably want to do it, and it makes sense that there's errors going from the negative side because it doesn't touch the axis. It's like an exponential graph. You know what I mean? But we do have other points. Stammer says this one probably cuts the y. You know? Let's see if it's true. But now I lost all my bloody values now. It just pushed me off, man. Anyway, so you want to have to draw that. I just lost my values now. But it should look. Yeah, I don't know if anyone has a values for me from 0 to 1. See if I can find graphs here quickly. But I lost my thing now. It's graphs.
It's the start 0 and the end 1.
Yeah, because it doesn't touch, man. It cuts. I just lost my values.
Oh, I have a lot of errors here.
Yeah, no, it's going to say error, and then eventually it's going to start to cut me. You know what I mean? From 1 onwards. I don't know if you see it there.
This is not a very user-friendly calculator, so I'll switch it off.
Is it the Casio?
Yes, but it's not mine.
Oh, I see. So it's not tough to draw, man. If you know the exponential graph, I'm going to show you now. You could have just done that basically. And I'll show you exactly what it looks like. I it's a stock graph what they're asking you to draw. Paste it for you, yeah. This is what I wanted to draw, colleagues. It just didn't come up. There we go. So that's what I mean. It doesn't touch it eventually at 1. You know what I mean? It goes like that. And you notice at 1 and 0, it cuts there. 2 and 1 gives you the next value, the next value, the next value. Can you guys see that?
Yes, sir.
Yes, sir.
Yeah, that's what I mean. So it won't, on the negative values, it won't touch nothing. It doesn't cut it all until it gets there. So even if you lost, you know it'll start over here, and you just have to extend the graph. So like I said, it's the inverse of exponential graph. Now, the thing is, I can show you how to convert between the two, but I don't know if you guys did logs, man. That's the thing, man. So I don't want to confuse you guys. But the exponential graph of this one, okay, Looks like that. And it should be, if I'm right, y equals e to the power 2x. I could be wrong, but no, it's not e, It's not ln. It's not ln, but something along that nature. Okay, so that's the first one. Not difficult. Just use the calculator to get the tables, or you can do it manually, of course, right? They want the neat graph of this over here. Can anyone identify what graph is this here? The y squared and the x. What's going on over here? What do you think? What do you think? What graph this is?
Straight line.
No, man. This one here. This here. How can it be a straight line?
Oh, that one.
Yeah.
It's kind of a semicircle thing. I don't know to what
Yeah,
side.
exactly.
Yeah.
So if you carry over, or what can we do? We can square everything here, right?
Yeah.
We square everything. Not a tough section, man. You will just know what to do. X squared, obviously this will be plus 16 minus y squared equals 0, right? We have x squared minus y squared equals 16. Am I
Is
right?
it minus 16
Negative
now?
16.
Negative 16. Negative 16.
Yes.
Yeah, there we go. Negative 16. Okay, but this is a bit of a problem because we
Because it's for the
don't.
plus and minus.
Yeah, we don't want that, especially we're gonna root. Let me just quickly see something. The other option is carry over. Yeah, it's okay. It's okay. Let me just quickly see. I want to put it into the standard format. You know what I mean? Before I actually.
So take away the negative.
Yeah, but then I'm gonna have the x being negative, and let me just verify something. That's fine. Just want to verify something. I'm putting my brain is tired now. Y squared, it's the radius. To make sure. Oh, the general form is y equals. Yeah, y equals r squared minus x squared, or y equals. Okay. Yeah. I don't want. That's going to be for semicircle. For circle, it's going to be circles like this. All right.
But can't you put the negative in front of the square root?
You mean over where? Of what square root?
When we do we let y 0 and then we do x and then we get negative square root 16, but a negative in front of the square root.
So you mean like changing all the signs like this? Is this what you're asking?
No,
What? Was that?
it's like minus 1 times 16. It's also minus 16, and then we leave the minus 1 and then we do the square root of 16, which
But then
is
you must
4.
but then if you times this by minus 1, everything must be times by minus 1. You know what I mean? If I do this side, each term must change signs. I don't know if that's the same thing. But this, to me, on surface value, it looks like a semicircle of some sort, right? Let me just, I don't know if you guys agree with me. But in a difference, it looks like some kind of inverse of it. So x, if I carry the whole thing over, it look like this. 16 minus y squared. This is what I'll show you what I'm basing it on. But obviously there is.
But so I think I'm right if we do the minus, because then we're going to get minus 1 times 16, and then we're going to get minus x on the one side and plus y on the one side.
Okay, let me just quickly follow your train of thought here. So we're happy with the squares over here, right? Is that fine?
Yeah, because we still don't know what side of the it's going to be positive or negative.
No, sure. It's just fine like this, right? You agree with this part? Are you there?
Yes.
Okay. Are we happy with this? Like this, right?
Yes.
That's it. Okay. And then?
Mm.
Oh, but just, okay. And then 16 what? Well, what do you do then?
No, we still go x squared minus y squared equals to minus 16.
Understood. Yes. Honestly, where are you taking this?
I don't know where I'm going with this. I'm just saying.
Yeah, but it's negative 16. The thing is, I don't want the negative 16 to be here. There's a particular reason why. Because you can't root a negative number, technically. Obviously, it's a complex number. That is what I'm not saying.
But if you go to semicircles, the general
Yes.
form for x
Oh,
on
you-
the negative
the
side.
root on the other
Yes,
side. Yeah.
yes.
It's like this. This is what I was doing now. That's like this.
Yes.
Yeah, that's different. Yeah, no, that is correct. Yeah. So that I was gonna be doing this next anyway now. Yeah.
So I wasn't saying it right.
Oh, okay. Yeah, that's fine. So you're just carrying over the whole thing to the other side. So that is definitely a semicircle. And then obviously all we have to basically do is what I would have done is again now is just the radius would typically be this value over here, but we can obviously prove this easily to find x. What happens now? You make y 0, right?
0.
So we do that, you get x equals negative root of 16, which will be negative, but wouldn't it be a plus minus now anyway? Oh, anyway, this is going to be root of 16 is 4, no?
4, yes.
Is it plus minus
It's plus
4?
minus 4.
Yeah, that's, that's a bit strange. Okay, keep it like this. But I mean that I will just keep it like that for now to find y. You make x 0. And then here we're going to have 0 equals root of 16 minus that, negative. Then divide by the negative 1 and 0, that's going to be 0. We're going to root the 0, it's still going to be 0. And then in the end, we're going to have 16 equals y squared. And then y squared also plus minus
16. 4.
Yeah, am I right?
Mm.
So then again, if you draw the thing, what we are getting here is, let me see, just draw a line. So,
but for the semicircle, we're only going to go on the one side. We're not going to have another x.
I was going to say that, yeah. We're just going to have to go from, so the positive graph is like this, the negative graph should be, let me just verify, I keep on forgetting. Yeah, the negative graph should be on the other side. So the negative graph is something like this. There we go.
Question, isn't a negative outside the square root stating whether it's going to be on the negative side or the positive side for the semicircle?
Yes, so let me quickly show you if like this is now y equals what's it, r squared minus x squared, right? This graph, and then you get the opposite of this graph, which is r squared minus x squared. There we go. So I think, colleagues, when you see a root, think about the, so this is the positive, think about the semicircle. This is this one, are you with me?
Yes.
And this one is
to the other side.
Am I right? No, I'm
no, you're doing it wrong. It must be on the y, yes.
Yeah, like this. That one's like that. The other one is like that. There we go. And this one is x equals r squared, y squared, right? Which we have now, or something similar. The positive one is like this, and then x equals negative, right? R squared, y squared, and that's going to be like that. Yeah, there we go.
So am I right by saying that first negative before the square root is on the other side?
That is correct, yeah.
It's an indication that it's supposed to be on the negative side.
Yeah, that's correct, yeah. One will be on the positive side, one will be on the negative side. So we can see over here, it's positive on the top, negative, positive on the top, negative at the bottom, right? Where x is negative. Y is positive there, and then y is, this is quite strange, negative on the other side. This doesn't make full thinking sense. But anyway, so this graph will look like this, like that. And we're going to have 4n,
minus 4. And then minus 4 on the x. Negative
minus
4 on
the,
the negative 4.
Negative 4. You see, this is what that was about here. Negative 4. Thank you very much. That's where I'm with. So root, I guess we just take the actual value. You see what I'm saying to you? Yeah, perfect. So just root 16 is just going to be a complete 4. So yeah, even now she's dead quiet there. Yeah, that's
No,
that.
no,
I feel like I'm talking too much.
no, no, I'm
No,
following.
no, carry on, carry on.
Okay, so that's done. Again, if you see a root, think of a semicircle. It's probably going to be a lot easier. Thanks to helping me for that. I was taking it a whole other route here. And then
I was
1.2.1.
doubting myself there.
Nah, don't. The sharp is working. Um, is a graph function or relation? You should know by now, right? You draw a line here. What is it? Cuts it twice. The vertical line test. Remember that one?
Yes.
So,
Relation, right? Get two
Relation,
outputs. Obviously, it's continuous, am I right? You don't lift up the hand, right? Continuous
yes.
graph. It's another mark for you. Then over here, you can see that's fairly easy, man. It's just some straight line. I know this is a parabola, no? You times a y on the other side, I think. But again, it's all just, you see when this one, we do this one over here.
Which one?
This one here, x plus y.
Didn't we do something similar earlier?
Yeah, that's what I'm saying. Those are the intercepts there.
Mm.
So you can just do that. This one is a hyperbola. I think obviously it comes with practice as you go. Like for number 2, I'll just declare values, man. That's what I'll just do. Like draw a neat graph. I'll just make a table on the calculator and I'll just follow this graph. Because all I want to see what the graph looks like. But I know this is hyperbola because if I times both sides by y for each thing, I have xy equals plus 4 equals 0 and xy equals -4. So I know that's a parabola already. You know, I mean, not a parabola, hyperbola, sorry. You know the one like this? Remember that one? That one. So I know it's like that already. I'm not going to do that one. X plus y over 2. Remember we talked about intercepts here. Those are the intercepts. Another way of, if you want to put it in the standard form, if you want to be more comfortable, you just do 2 times 3. 3 times x plus 2 times y equals 1 times 6 on the other side. So you have 3 plus 2y equals 6. Put in the standard form, it'll be 2y equals minus 3x plus 6. Divide everything by 2, you have -3 over 2x plus 6. And obviously from, not 6, it's going to be 3.
3.
From this, you can tell that's a negative graph already. And you can just, you know what I mean, substitute x, substitute y, etc., etc. But obviously, you can do it already here. Make x 0, solve for y. You know what I mean? Make y 0, solve for x. And you can draw a graph. But obviously, this graph would look like this. The x-intercept is what? 3, right? So it must go something like, it must cut it like that. It must be 3 over there.
Is the x-intercept or y-intercept?
This is the y-intercept.
Yes.
Yeah. I'm saying it cuts it here.
C is y.
Yeah. And we know it's going to be -3 over 2, but it must go that way. You know what I mean?
Gradient.
Yeah. I mean, for 2 marks, they don't expect this calculations and stuff. But so I just think with enough practice, maybe do around 4 or 5 question papers. You eventually can pick up the patterns of what they request. You know what I mean? So anyway, colleagues, I'm going to check for one more, but I don't think I'm going to do it. So I just want to have a browse to it quickly. And we're basically at the end, hey?
Is this the last class?
Yeah.
Or we're having class on Friday?
No, we're done. You guys said you wanted the class on Monday. I gotta focus on
I thought this was an extra one.
Yes, you know. Can't come right. You cannot say anything. But I think maybe next semester I'm gonna ask him, because I was new to teaching the maths. Not new. I mean, I've taught math obviously before, but what I want to say, I mean, I taught strengths before, but I thought I want to come do maths. But I think the guys next year will get the best of me when I teach. Okay, anyway, guys, I think that's it, man. I don't know if we need to do more functions. If Richard can motivate me, then maybe.
Richard is busy during the day.
Yeah. The only two things which I think which is I've missed is the factor theorem for the X cube graph stuff. You might have if possible, but what I suggest, go over a lot of the stuff, no? Like go over a few past papers and see if you're able to manage. You know what I'm trying to say? I'll take it from there. So I need to focus on strengths as well, but it's not tough, this particular section. I could have done some revision on some stuff you guys had problems with anywhere, basically. But this is a soft section, in my opinion. But okay, guys, hope you learned something. Eh? And yeah, hopefully I'll see you guys again
On Friday.
No, hopefully. I didn't commit.
I think we can vote.
No, there's no votes. This is not the parliament, but
But we can still ask in the group and then you will help us.
no, for sure.
Okay.
Like I'm not sure what section you guys are struggling with. Holistically. I don't think function is a big problem. I don't know. I don't think so. But I do think that others is the problem. Differentiation and so on. I don't know what you guys have to say about that. Because I marked your scripts.
I'm kind of coping.
Okay.
I don't know about the rest.
I marked people's scripts and I saw even module 1. And I was like, yes.
Did you mark mine?
No. I didn't, unfortunately. So I don't know, man. I don't know what I'd rather do some proper revision and go over functions, I know functions is easier.
So are we doing functions on Friday?
I don't know. I said I don't know. I can do functions, but I don't want to do functions because I think it's super easy. If I will do a session, it must be on other stuff, you know what I mean, which is more pertinent.
What is that? Module 6. Integration. Let me just get this.
So Richard, I don't know what you have to say, and Tanukazi,
Richard must back me up, please.
Yeah, look, no, I missed the integration session the other day, so we can maybe touch on that.
Yeah, I agree also. Yeah. Integration.
Okay.
On Friday, the guys.
We'll see.
Thursday or Friday, whatever source available.
Yeah, but
Vision.
Tanukazi, yes. Sorry.
Or maybe we can do the whole paper revision. Revise it.
Yeah, this is standard behavior of a certain demographic or not, you know what I mean. I don't want to say stuff here. I don't want to say anything on it. But are you guys good at differentiation? I'm just checking, man.
Kinda. We missed a few sessions in the beginning. And then after test week 1, we didn't have class the Friday evening or the Saturday. So we missed, and with test 2, we missed also 2 classes. So
what I'm trying to do is like just if I want to spend the time, I want to make it worth it, you know what I mean? And I don't mind going integration is, and it's gonna be fine. I can go over that. That's not even a problem. But I'm just thinking things in differentiation. When I marked, I thought it was sorted, but it seems like people are not. Like your product rule, you know what I mean? You guys do that already. Product rule and quotient rule, chain rule. You know what I mean?
Out on our own. So
okay.
Maybe that's why it didn't look so good. But yeah, I would really appreciate it. I don't know about the rest.
So I'll see you.
Let us work a couple of things there, and then we decide by latest Thursday, and then we ask you to then do something what we all agree on, which is that.
That's fine. I'm just looking here. I see chain rule is there. People are betting on chain rule, but where's the? Okay. Let me just stop the recording for now. I don't want it to peak. Okay. Yeah, okay, integration, no problem. You guys can let me know, but I support that go over.